We've studied the theory of electric current, and now this week we'll consider an application of that theory to circuits. This will be direct current circuits. And later in the semester we'll consider alternating current circuits. So this is chapter 26 in the textbook by Bauer and Westphal. And part one will be on the theory. So electric currents flow in circuits. And that is the physical basis for all the electronic devices that we use every day. Now, when I say direct current circuits, what I mean is we'll consider circuits with batteries and resistors and capacitors. And these circuit elements are connected by ideal wires. When I say ideal, what I mean is the wires will assume have negligible resistance. So this kind of system, these DC circuits, support what's called direct current, DC. In other words, it's current that flows in only one direction in any wire in the circuit. So if I have a wire in the circuit carrying a current I, the current will only flow in one direction along that wire. That's different from alternating current circuits, AC circuits, where the current oscillates back and forth along any wire in the circuit. It's alternating, sometimes moving to the right, sometimes moving to the left. Here's an example, a circuit diagram for a flashlight. So we have a battery with some electromotive force, EMF. And we have a switch. We can turn the battery on and off. And we have a bulb. The bulb has resistance. The bulb is made out of a wire, probably tungsten, which has a fairly high resistivity. It's a conductor, but it has a high resistivity, and so there will be a lot of energy conversion occurring in the bulb. We'll be converting the energy of the battery into light energy. The unit of electromotive force is the volt. The unit of resistance is the ohm. And when the switch is closed, current will flow around the circuit. The way this diagram is drawn, it'll be a clockwise current because this is the high potential side of the battery. This is the low potential side of the battery. And so there'll be an electric field in the direction from high potential to low potential, driving a current clockwise. Now, of course, that current is carried by electrons being negatively charged. Those electrons are traveling counterclockwise. And there's nothing in this battery which would allow the current to reverse, so it has to be a direct current. This parameter of the battery called electromotive force, EMF, it's a potential. It's the potential difference between the high potential electrode and the low potential electrode, the positive and negative electrodes. A battery is a chemical reactor that maintains a constant potential difference between two electrodes, the positive and negative electrodes. And electromotive force, it's not a force. It doesn't have units of force. It's an electric potential. So the unit of electromotive force, EMF, is the volt. All right, now to analyze circuits, we use Kirchhoffs rules. So this is the first section in chapter 26. In general, an electric circuit is a network. There are paths and junctions. A path may be an ideal wire. When I say ideal, I mean it has negligible resistance. Or it may have one or more circuit elements along the path. And we're considering batteries, resistors, capacitors, and switches. So if they're connected in series along a path, then they're part of the path. So those are the paths. And then a junction is a point where three or more wires are connected. So here's an example. This is a circuit with 5 circuit elements and 2 junctions. So here are the 2 junctions. And the paths are paths from one junction to another. And here's a path which has 2 circuit elements on it. These 2 dots represent resistors or batteries or switches. Here's another path, goes from one junction to another, with 2 circuit elements along the path. Here's a path which has only 1 circuit element along the path. Now, you can imagine that in general, these circuits could be very complicated. I mean, you could have an arbitrary amount of connectivity within the network. But we're pretty much interested in analyzing the physics, so we'll deal with circuits, networks, not much more complicated than this. All right, now, there are 2 Kirchhoffs rules. There's the junction rule, which says that at any junction point in the network, the current flowing into that point must be equal to the current flowing away from that point. So here would be a junction, and we could have current flowing along this path, and we could have a current flowing along this path, call that I3, and we would have current flowing along this path, which we could call I2. So I say I have current I1 going into the point P, and you have currents I2 and I3 going out of the point P. Well, according to Kirchhoffs' junction rule, I1 has to be equal to I2 plus I3. Or here's another picture. With I1 coming into a junction, I2 going out and I3 going out, then I1 has to be I2 plus I3. Now you could have more complicated junctions. You could have junction of 4 wires coming together. And you could have different directions for these currents. So when we start to analyze a circuit, one of the first things we do is we make a guess for the directions of all the currents. You know, some parts of the network will have current flowing to the right, some will have current flowing upward, some will have current flowing to the left. Well, we kind of make a guess as to which direction the current will be in each part of the network. And then at each junction, we have to have the junction rule satisfied. If it turns out our original guess for the direction of the current is wrong, that doesn't matter, because when we finish analyzing the circuit, we'll just find that the current that we calculate is negative. So if we guessed that a certain current was, let's say, to the left, but we did the calculation and found that the current to the left is negative, That just means there's a current to the right. Now, why is the junction rule true? Well, it's an example of conservation of charge. Electric charge is conserved. That's a universal conservation law of nature. Charge does not disappear, or it's not created nor destroyed. It's constant. So, unless there were some capacitance here where the charge would be building up at this point, but these are ideal wires, so that wouldn't be true. Any charge which comes into that point, the same amount of charge must go away because the charge at that position remains constant. All right, so that's the junction rule. The other Kirchhoff rule is Kirchhoff's loop rule. And it says that if you look at any closed loop, closed combination of paths within the network, the sum of potential differences around that circuit, across the different circuit elements in the circuit, must be zero. So let's suppose I have, in some complicated network, a closed path like this. It follows along in some direction and then comes back to the very same point where it started. Now, some parts of the path may just be ideal wires. Some parts of the path may have circuit elements. Some parts of the path may even have more than one circuit element. So I've sort of drawn this as if there were 5 circuit elements around this path. Or we call it a loop. Now, according to the loop rule, if I go around this path in either direction, either clockwise or counterclockwise, but let's say I'm going to go around the path in the clockwise direction, the sum of the potential differences across the circuit elements must be 0. So delta V1 plus delta V2 plus delta V3 plus delta V4 plus delta V5 is equal to 0. The sum of all the delta V's is 0. Now, we have different kinds of circuit elements. We have switches, but a switch makes this an open path. So there wouldn't be any circuit, there wouldn't be any closed path, there wouldn't be a loop which could carry current if there were a switch here. So the other possibilities are batteries and resistors. So what's delta V for a battery? Well, delta V for a battery is either plus or minus the electromotive force, EMF, of the battery. You know, a battery is a little chemical reactor that maintains a constant voltage difference between its 2 electrodes. So this is the high potential side, this is the low potential side. And the change in potential, if I'm going this way, is from low potential to high potential, so the change is positive. Because the change in a quantity is the quantity at the back, or at the back end, minus the quantity at the front end. So it's the output voltage minus the input voltage. Well, the output voltage is high, the input voltage is low, so the change is positive. On the other hand, if I were to consider the change in voltage across this battery, and I'm going across in this direction, I'm going across from the high potential side to the low potential side, then the change in potential will be negative. So you see, for a battery, the change in potential can be either plus or minus the electromotive force of the battery. And which sign, it depends on which direction you're going across the battery. So, I could consider a clockwise loop, but I could also analyze a counterclockwise loop, and so that would correspond to different directions across each of the circuit elements. So the numerical value is simple. It's just the electromotive force of the battery. It's just the battery maintains a certain potential difference called the EMF. And that's not changing, so that number is simple. What's a little tricky is the sign. Now, what about a resistor? All right, so that was for a battery. Now let's consider a resistor. Suppose I have a resistor, and suppose there's current going this direction. And suppose I'm analyzing the change in potential in this direction. Well, this must be the high potential side, this must be the low potential side, because the current will flow from high potential to low potential. So this has to be the high potential side if the current is traveling this way. And therefore the change in potential is from high potential to low potential. This potential difference has to be negative from high potential to low potential. But on the other hand, if I were analyzing the change in potential in the other direction, this would be from low potential to high potential. So here, the change in potential would be positive. So the value is simple. It's just I times R by Ohm's law. According to Ohm's law, the current is the potential difference divided by the resistance. But now you have to figure out the direction. Well, it can be either plus or minus. And it's a little tricky because it depends on the direction of the loop. It also depends on the direction of the current. If the current were in the opposite direction, then these signs would be opposite. So for a resistor, it'll always be either plus or minus IR, and the trick is to figure out the sign. And finally, we have capacitors. So here's a capacitor. Now, there'll be current going into the capacitor, but that doesn't determine the voltage difference. What determines the voltage difference is the charge on the capacitor. So let's say this side of the capacitor is a positive charge, and this side of the capacitor is a negative charge. Because a capacitor has always two conductors with equal but opposite charge. So if Q is positive, this is the high potential side, and this is the low potential side. High potential is where the positive charge is. Now, if I'm going across this capacitor in this direction, the change in voltage, well, it's from the low voltage to high voltage. So the change in the voltage is negative. But on the other hand, if I'm analyzing the circuit by looking at the change in voltage in this direction, from the high potential side to the low potential side, then the change in voltage there would be negative. Oops, this change of potential should be positive because it's from the low voltage side to the high voltage side. So the change in voltage is positive minus negative. It's positive. So again, the value of the change in the potential is simple. It's the charge divided by the capacitance. But the tricky part is what's the sign? And that depends on which direction you're going around the loop. It also depends on what your guess is for the charge on the two plates. If you made the guess that this plate is positive and this plate is negative, then this would be the change in potential for these two directions. But if you made the assumption that this side was positive and this side was negative, then these signs would change. Now again, if you make the wrong guess, it doesn't matter because it just means that when you finish the calculation, you'll find that the charge is opposite from what you guessed. So you'll get the right answer even if you make the wrong guess. But you have to be careful about the sign. So what sign? Well, it depends on the direction of the current, the direction of the loop, the orientation of the battery. You know, is the battery in this orientation or is the battery in this orientation? That will make the change in potential different than this orientation. And it also depends on the charges on the capacitor plates, which you don't know when you start doing the calculation. So you have to make a guess. So you make an educated guess, and then you calculate the change in potential based on that guess. So it's tricky. Analyzing circuits, what makes it tricky is to get the signs right in the changes of potential. Now, Kirchhoffs loop rule says the sum of all the changes of potential must be zero. Now, why is that? Well, that's because we assume that in a DC circuit, every point in the circuit has a certain potential. So let's take this point right here. There's a certain potential there. Now, if you go around a closed loop, there'll be changes of potential. There'll be 5 changes of potential. But you come back to this point, it has to be the same value that it started at, because this has a unique value of potential at this point. So that means whatever these changes are, they have to all add up to 0. And that's Kirchhoffs loop rule. So, well, we'll work out some examples. But, you know, there's a table in chapter 26 which gives you rules for getting the correct signs. So study that table and also study some examples, both in the book and we'll go over a few here in the screencasts. Really, the subject of circuit analysis is tricky enough that the only way you can really grasp it is by doing some examples. So let's consider an RC circuit in which a capacitor is being charged by a battery. So we have here a battery and a switch. Well, that's just for turning on or off the current. We have a resistance and we have a capacitance. And we'll say that originally the capacitor is not charged. But then we close the switch. Current will flow. Current cannot flow from one plate to the other because the two plates are separated by an insulator. So what happens at the capacitor is that charge begins to accumulate on the two plates. Equal but opposite charges will accumulate on the two plates. So let's say we close the switch at time t equals 0, and we'll calculate the capacitor charge, Q at time t, and the current, I at time t. So these will be functions of time when t is greater than 0. And that's our goal, is to calculate Q of t and I of t. Now this is a single loop circuit, which is one loop. So there are no junctions. So all we have is Kirchhoffs loop rule around this one single loop. Now let's close the switch and let's imagine what's going to happen. Well, this is the positive side of the battery. So current I will flow in this direction. And current I will flow in this direction. This is the positive side of the battery. So it's like positive charge will flow away from the positive charge of the battery, and negative charge will flow into the negative electrode of the battery. Of course, you know it's just the electrons that are flowing. So it's actually electrons will flow out of the negative side of the battery, and electrons will flow into the positive side of the battery, so that the battery can continue its chemical reactions inside. But in terms of the conventional current, because electrons have negative charge, we say there's a current flowing away from the positive electrode and into the negative electrode. And that current continues through the resistor and up to the capacitor, but it can't go through the capacitor because there's an insulator. So a charge will accumulate on this plate, and a negative charge will accumulate on this plate, because the capacitor itself will have net charge 0. So let's think of the flow of electrons. As electrons are flowing, counterclockwise, they accumulate on this plate. That plate becomes negatively charged. That pushes the electrons on this plate away, because like charges repel. So the electrons will be pushed away, corresponding to a current into this side of the plate. So in the end, the capacitor plates have equal but opposite charge. Now you see how I've sort of guessed that there'll be a clockwise current, and the right side of the capacitor will be positive, the left side will be negative. And now let's apply Kirchhoffs loop rule. All right, so we define I of t as the clockwise current. And we'll define Q of t as the charge of the right plate of the capacitor. Then minus Q of t is the charge of the left plate. Kirchhoffs loop rule says, as I go around the loop, the changes of potential add up to 0. So let's start at this point. If I go up here, the change in potential is E, the EMF of the battery. So there's delta V across the battery. Now there's no change in potential across an ideal wire. We assume the resistance is 0. But now as the current goes through the resistor, there's a change in the potential. This has to be the high potential side to push the current in this direction to the low potential side. So the change in potential is negative. It's negative IR. And then finally, I have the change in potential across the capacitor from the positive side to the negative side. Well, the positive side is high potential. The negative side is low potential. So the change in potential is negative Q divided by C. So that's the equation given by Kirchhoffs loop rule. And, E, I, R, Q over C, those numbers are kind of obvious. What's not so obvious are the signs. So be sure that you understand these signs. Now that's one equation for two unknowns. The two unknowns are Q and I. So we need another equation. Well, the other equation is I is equal to dQ over dt. Here's current I. What's the definition of current? It's the amount of charge passing a point, let's say passing this point per unit time. So in time delta t, the amount of charge that passes that point is I times delta t. That's the amount of charge that accumulates on this side of the battery. So that's delta Q. So delta Q is I delta T. Or I is delta Q over delta T. We take an infinitesimal time. I is dQ dt. Remember, I and Q are functions of time. So this is just an equation for the derivative of Q. The derivative of Q with respect to time is I. dq dt is the rate of charge accumulating on this plate. That's the rate of charge coming in the current. So that's I. All right, so what we have here are differential equations. I can substitute this in here for I, and you see I have a differential equation for Q. Now, whenever you have a differential equation, you also need a boundary condition. What's Q at time 0? So, as in any mathematical problem with a differential equation, you need some boundary conditions. In this case, it's the boundary at time 0. This is a differential equation in time. What happens at time 0? Before the switch is closed. Well, we said before we close the switch, the charge on the capacitor is 0. In other words, we're charging up the capacitor. So Q of 0 is 0, and that's the boundary condition. So substituting for I here, we end up with this differential equation, dq dt. Well, let's change all the signs. Let's move e to the other side of the equation and change all the signs. So we have IR. Let's divide through by R. So we have I, that's dq dt. I change the sign, so plus Q over C divided by R is plus 1 over RC times Q is equal to minus E. I change the sign, so that's plus E divided by R. So I really have these 3 equations, but I can eliminate I using the second equation, and then I just have this equation with the boundary condition. I hope you're taking notes and trying to repeat the calculation in your notebook. You should find dq dt plus 1 over RCQ equals E over R. And again, you have to make sure all the signs are right. The equation we had on the previous slide, dq dt plus 1 over RCQ is E over R. Well, the rest is just math. We need to solve this differential equation. Now, it's a simple form of differential equation. It's called a linear differential equation. And there are various methods for solving differential equations like that. Let me just sort of work through this one step at a time. If we had not E over R, but just 0, then we'd have the equation dq dt plus 1 over RCQ is equal to 0. And everybody knows the solution to that equation. It's an exponential. Q would be e to the minus t over RC. Because if you differentiate the exponential, you get the exponential back again times minus 1 over RC by the chain rule. So dq dt would be minus 1 over RC times the exponential back again, which is Q. So I'd have minus 1 over RCQ. And here I have plus 1 over RCQ. So they'd add up to 0. So this would be the solution if E were equal to 0. But E is not equal to 0. So I have to find a solution where E is not equal to 0. Well, there's an obvious solution when E is not equal to 0. It's just a constant solution. Q equals C times E. Because C times E is a constant. E and C don't change in time. So dq dt would be 0. And this would be C over E divided by RC. So this is a solution. If E is 0, this is a solution if C is not equal to 0. Well, okay, of course I can't just add solutions, but I can make a good guess. I can say, let's try this. Let's try a constant C1 plus another constant C2 times e to the minus t over tau, where tau is RC. So you see, here's my exponential e to the minus t over RC, and I'll define tau. Tau will be an important quantity. I'll define RC as a quantity tau. And I could add a constant, because I know if e is not equal to 0, one solution is a constant. So this is a good guess. Well, now let's calculate dq dt. Well, this term is the derivative of 0. This term, it's minus 1 over tau, c2 e to the minus t over tau. The derivative of the exponential is the exponential back again times minus 1 over tau by the chain rule. And now this term is 1 over tau, RC is equal to tau, 1 over tau, then q. C1 plus C2 e to the minus t over tau. That has to be equal to e over r by this equation. So if I look here, well, these two terms cancel. The terms proportional to C2 cancel. And that's just a statement that if e were equal to 0, the exponential solves the equation. So those two terms cancel. No matter what C2 is, those two terms will cancel. Now, the other term is this one. C1 over tau has to be e over r. So in other words, C1 has to be CE. C1 divided by tau is e over r. So C1 is e times tau. Tau is RC divided by r. The r's cancel. I get c times e. All right. So that means I have found a solution to the differential equation. In fact, I've found an infinite number of solutions to this differential equation. They all have to have this value of C1, but they can have any value of C2. So the differential equation does not determine the solution, because there's this possibility of different values of C2. What determines C2 is the boundary condition. The boundary condition says q of 0 is 0. Now here's my q of t. Set t equals 0. The exponential of 0 is 0, so q of 0 is C1 plus C2. So C1 plus C2 has to be 0. So in fact, there's only one solution that satisfies the boundary condition. That's where C2 is equal to minus C1, and C1 I figured out had to be C times E. So now I know what C1 is, now I know what C2 is. So here's the solution. C1 is CE plus C2. C2 is minus CE, so minus e to the minus t over tau. So there's the charge as a function of time. If you've had a differential equations course, you know how to solve this kind of equation. You have the particular solution, that's the solution CE, plus the solution of the homogeneous equation, that's the exponential, and you have to apply the boundary condition. Well, that's exactly what I've done here. So here's q as a function of time. And I hope you're taking notes, because you're going to run into this kind of equation again on some of the ln kappa problems, and you'll have to use this same trick, the same method for determining the solution. Now I also want to know the current, but once I know the charge on the capacitor, it's easy to figure out the current. I is dq dt. So dq dt, well, this term is a constant, so the derivative is 0. This term will be minus e to the minus t over tau times minus 1 over tau by the chain rule. The minus times minus will cancel, so I'll get plus CE divided by tau, e to the minus t over tau. And remember, tau is RC, so this is e over r, e to the minus t over tau. So there's the current. So the current obeys exponential decay. Let's make graphs of these functions. So here's the current. The current obeys exponential decay. So the current is a function of time. At time 0, when I first close the switch, immediately a current occurs, which is equal to E divided by R. There's a kind of an instantaneous current, E divided by R. Volts per ohms is amps. So it starts here at I equals V over R. And then it decays exponentially. And eventually decays to 0. So the current flows for a while, charging a capacitor, but gradually the current slows down and stops. That's I of t. Now what about Q of t? Well, here's Q of t. It's this function. At t equals 0, it's 0. That was the boundary condition. So it starts out with no charge on the capacitor. Then the charge on the capacitor accumulates, and as t goes to infinity, approaches CE. So here is where the current is equal to C times E, or C times the voltage of the battery. And the charge approaches that asymptotic value exponentially. So as the current decays exponentially, the charge approaches an asymptote exponentially, which is just C times V. So what's the final state? Well, I have this battery. I have a resistance with no current, and I have a capacitor. Well, the charge on the capacitor will just be V divided by C. Q is V over C in the steady state. So this is the steady state solution. The steady state solution is Q equals, well, let's call it V over C. Or I could call it E over C. Yeah, I guess it would be more logical to call it E over C. That's the voltage of the battery divided by the capacitance. In other words, the capacitor is completely charged, and there's no current left because the battery is driving a current this way, but the capacitor is driving a current in the opposite direction. Those two currents cancel, so there's no current across the resistor. So this time dependence is called a transient. You get this transient time dependence. The system approaches the steady state, where Q is E over C. The capacitor is completely charged. But to approach that steady state, it has to start from the chosen initial state, which is different. And so the approach to equilibrium is called the transient. All right, so that completes part 1 of the screencast for this week. And now there'll be another part which gives some examples, some example calculations.